So welcome back. This is the second part of applying similarity, and what we're going to talk about today is the two transversal proportionality corollary. Now what we have here is we have two transversals, AE and BF, and we have three or more parallel lines dividing those things. It kind of looks like this. AB, CD, and EF are all parallel. Okay, and so that's what we're looking at here. The conclusion that we draw here, according to the corollary, is that if three or more parallel lines intersect two transversals, then they divide the transversals proportionally. And so what this gives us is AC over CE is equal to BD over DF. Okay, and so the pieces are now proportional because these lines are parallel and they're cutting transversals. Okay, we have an art application that goes with this. All right, and so let's look at this art example here. An artist used perspective to draw guidelines to help her sketch a row of parallel trees. She then checked the drawing by measuring the distances between the trees. Okay, and so these trees, pardon my lines, these trees are all representing these parallel lines. Well, we have three or more parallel lines that are cut by two transversals. Well, AD and KN are those transversals. Okay, and so what we are going to, AD and KN are those transversals that are cut by these multiple parallel lines. And so what we're going to check to see is, are these trees actually parallel? And so if we're going to find LN, let's see what we're actually comparing to. First of all, we need to know that AK is parallel to BL, is parallel to CM, is parallel to DN. So that's what we know right off the bat. And when we know that, what we're given is that then we have two transversals. Well, if we're finding LN, let's look at what we're finding, this piece here, we're going to test out certain things. And what we're able to say is KL over LN. So this top piece over this big piece is equal to, and we look over to the other transversal. Well, that's really going to be KL and AB corresponding. So AB over, and LN is this big piece, so this is going to be BD. I'm going to fill in what I know. Well, what I know is this. BD is actually equal to 1.4 plus 2.2, which is 3.6. And so when I fill this in, I end up with KL times BD is equal to LN times AB. Okay, that's the cross products property. Remember, these get multiplied and these get multiplied. Okay, let's fill this in. Well, KL is 2.6, so 2.6 times BD. Well, BD, let me fill that in as well. Should have done that already. Probably confused you there. BD we have, because BD is that 3.6, so 2.6 times 3.6 is equal to what we don't know, that LN, times AB. Well, AB is 2.4. And so what I'm going to do is, then I'm going to step over here and I'm going to say divide by 2.4. And what we end up that being equal to is that LN is 3.9 centimeters. Okay? So we just need to work on seeing those transversals in those parallel lines so that we can use this theorem. Well, what I'm going to ask you to do is find LM and MN. So LM and MN. I'm going to give you a hint that you might need to use the fact that these three lines here are parallel, and the fact that BC is proportional to a couple of these different things. Okay? So go ahead and try that, and we'll go from there. All right. The next theorem is the triangle angle bisector theorem. What we have given to us is that these two angles here are bisected. May not look like it in this diagram, but they are. Okay, so the angle bisector of a triangle divides the opposite side into two segments whose lengths are proportional to the lengths of the other two sides. What does this actually mean? It gives us BD over DC is equal to AB over AC. So AB over AC is BD over DC. This is really actually kind of cool because now we have one triangle and one extra line that gives us all of these relationships between things that don't even look related. Okay, so this is good for us. The way that we use this, if we're going to find RV and VT, we notice that this triangle has this angle bisector going on. And so I'm just going to fill in what I know. Well, I know that RV over VT is equal to, now, let's notice how this works. Up here, BD over DC. So the left side over the right side was equal to AB over AC. So notice BD and AB are connected. They are consecutive sides, adjacent sides. So if I'm talking about RV, I need to have SR first, and that's going to be over ST. Okay, so we use the pieces that are connected on top and the pieces that are connected on bottom. How does this work? Well, now we're just going to fill it in. So x plus 2 over 2x plus 1 is equal to SR is 10, ST is 14. I think the hardest part of this one is actually setting it up, because once we get into the setup and we cross multiply and divide using that cross product property, it's really just algebra from there. So let's look at this. I'm going to circle because sometimes I just like to do those kinds of things. 10 times 2x plus 1 is equal to 14 times x plus 2. I'm going to use the distributive property here and here to give me the cross product. So 20x plus 10 is equal to 14x plus 28. Okay, I've got this, equation here. I'll combine like terms, and you know what, guys? I'll even use a different color. Let's use a little bit of a red color here. Subtract 10 from both sides. 20x equals 14x plus 18. And I'll subtract 14x. I'll subtract 14x. 6x equals 18. So x is equal to 3. Now, I use that here, and I use that here because I want RV and VT. So RV equals x plus 2 equals 3 plus 2 is 5. So RV equals 5. That is the worst 5 I've ever seen. It looked like I don't even know what. VT equals 2x plus 1, and that's 2 times 3 plus 1, which is 7. So VT equals 7. Don't give up on the problem, guys. Just because you found x, you need to make sure you go through and you find what it is that you're actually trying to solve for. So in this case, it was RV and VT, so we're good. Okay? As you might have suspected, here's an example for you to try. Go ahead and look back at that theorem before, and look back at the previous example. Find AC and DC. All right, guys, thanks for watching this one, and we'll see you next time.